Hey guys, so I'm not going to go over the bookwork that's due today. I will go over that tomorrow in class. You're going to have a worksheet due tomorrow. I'll post that as soon as I'm done. It's 9:58. This will probably take me, I don't know, somewhere between 15 and 20 minutes, I would think. So yesterday we learned about collision theory, right? And basically there were two things about collision theory that I needed you to understand yesterday, and I'll just kind of explain that again really quick here. So, okay. So, collision theory. Whoa. Let's see what's going on there. We'll do this one. Okay. So, collision theory basically, if reacting particles don't collide, they don't react, right? And I use the analogy of an enzyme, right? With like a substrate. Let's say you have two particles and one kind of looks like this, right? So there's reactant number one and then reactant number two, reactant number one. It's not going to be perfect, but if this one, let's say it just looks like that. So like Tetris, if you know what that is, when these collide correctly, they will form the product, which would be, I can do better than that, which would do reactant one. Let's see. There we go. Right. So, and that would be your product, right? So, wow. Sorry, guys. A little out of it here. All right. So, reactant one and reactant two, if they collide with the proper orientation, then they will react and make a product. That was one part of this theory. The other part is if they don't hit each other hard enough, nothing will happen, right? So if I have these two particles and they collide with each other very lightly, then they're just going to bounce off, right? So let's color that one in. But if they hit each other with enough kinetic energy, sufficient kinetic energy, meaning it's moving fast enough, when they hit each other, they're going to stick. Something's going to happen and you'll make a product, right? Or let's say a compound if you have two elements, two atoms combining. So that was the gist of yesterday. So now there's more to it. There's these things called potential energy diagrams. So potential energy, diagrams. And sorry, that's supposed to be an M. Sorry, I'm extremely messy today. So what is a potential energy diagram? Well, if we go to our periodic table here, or our reference tables. All right, so if we go to table I, which hopefully you will remember, this one here. All right, and I'll just actually take a picture of this here, just so I can mark it up. All reactions have conservation of energy, conservation of mass, right? So if we look at table I, hopefully you remember all these negatives here mean they're exothermic, meaning releasing energy. And then all these positives mean they're gaining energy. So they are endothermic. So basically, if you look at this one here, I'll just use this as an example. Nitrogen plus oxygen, 1 mole of nitrogen plus 2 moles of oxygen produce 2 moles of nitrogen dioxide. This can only happen if you give it 66.4 kilojoules of energy. You have to give it some kind of, you have to give it energy, 66.4. Otherwise, this won't work very well. That's why it's endothermic, because you give the reaction energy in the beginning. It absorbs in the beginning, right? We would write this number over on this side. Where if you look at, I'll try and, these are kind of more, here, this one, more simplified than the other ones. So this one is exothermic, meaning 1 mole of nitrogen plus 3 moles of hydrogen will only make 2 moles of ammonia if it releases 91.8 kilojoules. So this is exothermic. The energy would go on the right side with the products. So this would release energy after it reacts, right? So this one absorbs energy, This one releases it. So those are opposites, endo and exo. Well, these potential energy diagrams are these graphs that show the energy change. And there's two types, an endothermic and an exothermic. Now, the only thing I want you to kind of get out of this video, because nothing's new so far, at least it shouldn't be. The only thing I want you to get out of this, and you'll be able to do the worksheet through tomorrow, is that both of these reactions require what's called activation energy. Think about when you want to activate, this is going to sound kind of silly, but activate your car or truck, right? You turn the key and there is an ignition or a spark plug that produces a spark, and then it ignites the gas, and then the car starts, right? So you have to have that ignition. You have to have that spark, and that spark is the activation energy to start combustion. And actually up here, here's combustion. And in fact, right here, this is the combustion of octane. This is octane. That's what happens in our car, essentially. So when you give it enough energy, a little spark to start that process, then it will release energy. Anytime you burn something, it releases energy. But anyways, the point I'm trying to make is all of these reactions on here have what's called a potential energy diagram. All reactions ever have a potential energy diagram. And activation energy needed to start it, is a big part of that. So that's what I'm going to try and show you here. And let me go to this this thing here. Where am I? All right. So let me take a picture of this. Actually, can I do two of these? Let me see. Sorry. I think I can. Sure. There we go. All right. So now, instead of me drawing these myself, I'll just use this from the interweb here. These are called potential energy diagrams. So sometimes they're abbreviated PE diagrams. And this is what you're going to see on the worksheet due tomorrow. So always with these diagrams, always you have potential energy on the Y, and you have either time or reaction progress on the X. And then they all kind of look like these little hills or little mountains. The reactants always start on the left side, and the products are always on the right side. Just like if you were to write a reaction, reactant yields product. So reactants come first, something happens, then there's a product, right? So that's nothing new. This delta H that you see is the change in heat, change in energy. So I'm kind of going on another path here, but it's labeled, so I figured I'd explain it. So tomorrow in class, I'm going to talk more about this, but this is the energy the reactants either lose or gain. So that's what this essentially is, which matches, where am I here? This one. This number is the delta H. Look, delta H, right? So basically, if you have an endothermic reaction, endothermic reaction, let me erase this. Okay. So we have an endothermic reaction or an exothermic reaction. The value of this here will always be found on table I, or it'll be given to you, right? So there's two things I want to get done here with this before I end this recording. Can you look at A, so graph A, look at graph B, and tell me which one is endothermic, which one is exothermic? Obviously, this is a video, so I can't ask questions. So I'm just going to tell you. But if you're looking at this and you say, all right, well, the y-axis is energy, right? So let's make up a scale. 0 down here, 0 down here. Let's say 100 up here, 100 up here. And let's say the units are in kilojoules, right? Kilojoules. So as we start here, or we start here, the reaction progresses, and then we end here. Reaction progresses, and we end here. So they draw these dotted lines for us, which makes it nice. The difference in where we start and where we end, I wish there was a dotted line here. The difference between these two lines, that's the delta H. And what is that? That's the amount of energy either lost or gained. So here, we start down here. Let's make up a number. Let's say this is 20. We react, we go up through this hill here, which I'll explain more. we end up down here as a product, right? So let's say you're starting here and you walk up the hill and you come down the hill, right? Well, you're ending up higher, more energy than you started. Let's say that's almost halfway. So let's say that's 50. So if you started with 20 and you end at 50, that means you gained energy, right? Energy is on the y-axis. You actually gained 30 kilojoules, positive 30. Whereas over here, let's say this is 50 and this is 20. If you start at 50 and you walk up the hill and then you come down the other side, and now you're standing here, you've actually decreased by 30. So that's negative 30. So this one is actually exothermic, and this one is actually endothermic. So if you do watch this, which I hope you do, you might be a little overwhelmed. Like, I don't understand. That's fine. I'm going to explain again tomorrow in class, but I'm just getting the ball rolling here with this. So these are called potential energy diagrams. And the bottom line is, and I'm going to erase this here, is if you start lower and end higher, that means you gained. That's endo. And if you start higher and end lower, that means you lost something in the process, lost energy. That's exo. All right, last thing. Right at the top of these peaks, that's where the reaction occurs. So that's where the collision theory takes place. So that's where the collisions are. So there's collisions there. Whoa, what did I just do? Oh, I see what I did. Collisions there. Okay. So right at the top, that's where particles, reactants are colliding. And if they collide with enough energy and they have proper orientation, they make products. Same thing over here. Well, in order for a reactant to get up to that peak, you have to give it energy. So from here to here, imagine you're standing here. Imagine you're standing here and you want to climb this mountain. The only way you're climbing the mountain is if you're using energy, right? You have to eat food, gain that energy, use your muscles, move your arms, legs, right, to climb a mountain. So there's energy involved with going from reactants to the top of the peak, from reactants to the top of the peak. This arrow here, the energy needed to get to the top is called activation energy, and I'll abbreviate just AE. AE. So activation energy is the energy required to start a reaction, like turning the key in a car. So once you get here, now reactions can occur. If you don't get there, right? Like think about rolling a ball up the hill. If you roll a ball and it just barely stops before it gets to the top, it's going to come back down to you. Same thing over here. So if you're rolling a ball and it gets just over the top, now it'll have enough momentum to carry on, right? Same concept here. That's what this is. If you give the reactants enough energy to get there, then they have a shot at colliding correctly and forming products. So that's called activation energy. And that's what the worksheet is on due tomorrow. Now, the only other thing I'd like to mention is, and I'll write the definition on the whiteboard part here, is that notice that this peak, let me erase it because it's getting kind of messy. Notice that this peak here, so from here to here, is a smaller distance than from here to here, right? So if maybe this is a change of, let's say, 30 kilojoules, maybe this is a change of like 60, right? So this reactant would get to the top of peak B faster than the reactants would get to the top of peak A. Why? Shorter distance, right? Imagine you're racing yourself. You clone yourself and you race yourself up the top, okay? One's here, and you start at the same time. The one in peak B here is going to get to the top first. It's shorter distance, right? So this reaction would actually happen faster. This would happen faster because less energy is needed to start that reaction. So activation energy needed to start a reaction. And the concept here is if you have lower, I'm just going to abbreviate, activation energy, that equals a faster reaction. which actually means an increase in reaction rate. So that means the collisions are going to happen faster and the reaction is going to happen faster. So again, if we look here, B is going to react faster than A. Has nothing to do with endothermic, exothermic. This distance is shorter. Once they get here, they can get over the hump faster. So this is going to be a faster reaction. All right. I'm sure you're a little confused. That's okay. Do the best you can on the worksheet. We will go over it tomorrow. And let me stop recording.